ij dli dot dlj over xi minus xj, current in loop I times loop j. And what I see in this expression is that there is a geometrical quantity here that depends on how the loops are oriented relative to one another in space. And this matrix here is called the mutual inductance. It's a geometric quantity. So, the potential energy associated with that current distribution can be written as 1/2 Lij times the current in loop I, current in loop j. Where Lij is equal to 1 over c squared I j over x I xj, which is equal to the mutual inductance. All right. Of course, there is a self-inductance of a given loop. And so if I only had one loop, then the potential energy of that one loop can be expressed in terms of the self-inductance of that loop. How do we understand the meaning of inductance? Well, of course, the meaning of inductance is how much current is induced for a given flux. Or said another way, if the flux is changing, how much EMF is generated around that loop. So, how does one typically calculate inductance? This is somewhat analogous to what we did in statics in terms of capacitance. Yeah?
Yes, I was just going to ask, so jumping back a little bit to the mutual inductance, is that expression for the energy, is it kind of analogous to, like, if you bring a bunch of point charges together, and that's just the energy to bring them together, and
Yes.
not the energy that's contained in the fields themselves, or each of the individual fields. So not, say the energy of the field surrounding this point charge and that point charge and that.
So let's step back for a moment.
Okay.
In electrostatics, we asked how much work was it necessary to establish a charge density rho. So we imagined that we had charge distribution at infinity, and as we moved it in from infinity, all the charges do work, feel the potential against each other. Eventually, I get them to the final distribution, and it took me some work to do that. And the work necessary to do that was the potential energy stored in the charge distribution, which we wrote in terms of the scalar potential like this. This is the self-energy. And this was equal to 1 over 8 pi E squared not to be confused with the potential energy of a charge distribution in an external field due to other charges. In the context of the magnetic field, what we've just discussed is analogous to this. This is the self-energy. Of course, in the context of the electrostatics, we had the embarrassing problem of the singular point charge. And we don't have that problem here.
Okay.
So this is, I imagine, there's no current in this loop, and then I, turn on the source and it starts, adiabatically, say, ramping up to the final current. I could say that the amount of work that was necessary to do that was the work I had to do against the back EMF that was being generated as the current was changing and thus the flux was changing, which can be equally expressed in terms of the self-inductance of the loop. This is equal to the integral over all space of the magnetic field that's created by that current distribution.
Okay.
In the same way that in electrostatics, we had that this potential energy was equal to 1/2 CV squared, where C was the capacitance and V was the final voltage. It's equivalent to either this expression or this expression.
Okay.
All right? Cool. All right, so right. So how do I calculate inductance? Well, similarly to the way that we typically calculate capacitance, we look at the geometry. Let's look at the mutual inductance for a moment. Let's say I have two loops, whatever they are. They don't necessarily have to have the same shape, but I seem only capable of drawing one kind of shape. And what I want to know is the following. Let's not put any current here. Let's say that I put some current here. It's going to make some magnetic field, B due to 1, which is going to flux through contour 2. All right? So the flux through 2 due to 1, this is the magnetic flux, is equal to what? Well, it's equal to the surface integral. If this is my contour, which has a particular orientation, and this is the normal, it's the flux of magnetic field 1 through surface 2. Okay? So that's the flux of the magnetic field through this loop due to the current flowing in loop 1. Now we just showed that the flux integral is equal to the contour integral of the vector potential, as we showed in one of those famous asides on the backboard over there. Okay? And so if we plug in again for the vector potential in terms of the current, that's equal to the contour integral through contour 1 of IDL1 divided by that dotted into L2. Which, according to our expression there, is equal to C times the mutual inductance between 2 and 1 times current 1. So we have an important expression here which says that the flux through 2 due to 1 is C times the mutual inductance between 2 and 1 times current 1. Of course, we have, doesn't matter what order I write this in, because this is symmetric, the inductance on 1 due to 2 is equal to the inductance of 2 due to 1, because this is symmetric between them. That is known in the electrical engineering literature as reciprocity. So, this is the relationship between flux of magnetic field, inductance, and current. With, unfortunately, in these units, this is one place where I really think suggests, you gotta give the props. I mean, this is not really, what the hell is the C doing here, but it's there. So. Because capacitance and inductance don't have the same units in CDS as I wish they did. So we have the self inductance as well, which says that the flux through, the magnetic flux through a surface, through a loop, or enclosed by a loop, is equal to the self-inductance times the current flowing in that loop. Times C. So what that tells me is that if I have a changing current, through that loop, that is equal to the rate of change of the flux according to this relationship, which is equal to minus 1 over C, which is equal to minus C times the EMF, right? Because by Faraday's law, the EMF is minus 1 over C, the change in flux. So of course what this tells us is that the EMF generated by a change in current is equal to minus L di dt. That's the famous relationship between a change in current and the inductance, which you know from your circuit theory. So, the way in which one calculates inductance is you have some geometry, you apply a certain current, you then calculate what the flux is for that current, and the ratio between that current and that flux is C times the inductance. So let's do a quick example. Let's look at the self-inductance of a solenoid. So let's say I have a solenoid, very long cylinder, it's got all these loops. All right? And it's got n turns per unit length. Okay, so I've got a density of turns here that are very densely packed. This solenoid has some radius over. Okay? And so the question is, what is the self-inductance of that solenoid? How would you do it?
You know the B field inside, right?
So what we said is that inductance is related to how much flux do you get for a given amount of current. So what you do is you put some current through the thing. Okay? And then I look at how much flux there is of the magnetic field through the thing. And then divide by that current, divide by C, that's the inductance in these units. So how much magnetic flux is there? So what's the B field associated with this current distribution? This is a solenoid. We should know. It's like a capacitor. You know, these are one of the few things we should know. Maybe we don't have our 4 pi's in C right. I'll forgive you on that. You can put them U not, and I won't even throw them. But what is the magnetic field? If you forgot, how do you get it instantly? Ampere's law, right? Everyone's going to study this because you have an exam coming up, right? Okay, so we're going to do Ampere's law quick. Here it is. The cross section of my solenoid looks like this. Dot, 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 dot. All these turns. I got current coming out of the board over here. I got current going into the board over here. Right? I know if it's an infinite solenoid, the magnetic field is 0 outside and it's uniform and in the direction. So what kind of amperial loop do I put? Yeah. Something like this. My Amperian loop. And the contour integral of B dot dl is then what? Well, B is only in this direction. It's uniform. It doesn't matter where I am. So it only contributes to this leg of the loop. So that's equal to D times L. Let me write this in a place that someone can see it. So, integral D dot dl. In this case, it's just D times that length L. And that's equal to what? Typically, there's a 4 pi in these things, right?
Over C.
Over C. So I enclosed over C. All right, and what's I enclosed? Number of loops times I, right? Which is equal to the number per unit length times L times I. So the magnetic field inside the solenoid is equal to 4 pi times I over C times N. Thank you. Also known as 4 pi the surface current over C. Just like 4 pi sigma for a capacitor. Or sigma over epsilon naught. Okay, sorry. All right, so what's the inductance, the self-inductance of the solenoid?
4 pi squared and R squared over C squared.
Right, so we've now got to just multiply this, the flux of the magnetic field, right, is what? Well, each loop it's in this case, because the magnetic field is uniform inside the solenoid, the flux of the magnetic field is just the area of the solenoid times the total number of loops, which would be n times whatever the total length is, assuming L is long enough that the fringing fields are negligible. It's a bad notation because that's the inductance. It's called, what did I call it in the notes? I guess I called it L again. Times B.
Wait, sorry, where are you getting the L from?
Because the total flux is the total number of loops. Each loop
I see.
contributes one flux, but we have little n times the total length numbers, the total number of loops. That's the total amount of flux. Let me just call this thing A, the area of the loop, because that updates. So I don't have all these damn pi's floating around. And so I have 4 pi, the area, cross-sectional area, n squared L over C times I is equal to C times the self-inductance times I. So, the final answer, please. The self-inductance of a solenoid, L, is equal to 4 pi A n squared L over C squared. Okay. All right. So, before we conclude here, of course, we note there's been a bit of a sleight of hand in this whole discussion today. Because when I calculated the energy, for example, necessary to create this current distribution, notice what I did. Let's go back over here. I made this substitution. Remember that this relationship between the magnetic field and the current was only true for a steady current. Right? Because this was the magnetostatic relationship. That is to say, this relationship, Ampere's law, del cross V is equal to 4 pi J over C, implies del dot J is 0, which is to say the current density is constant. But we didn't have a steady current here. We made it non-steady. So we kind of cheated. What we have currently, let's go back to the sideboard over here. So far, we have the field equations. We have del dot E is 4 pi rho, del dot B is 0, del cross E is no longer 0. We have the Faraday law, negative 1 over C dV dt, and Ampere's law. Ampere's law implies del dot J is 0, which means that the charge density must be constant. So, as you know, these equations are incomplete. And this was the amazing, I think, beauty of this whole theory. And here you have, when you think about it, in the history of the development of electricity and magnetism, you know, back in the 18th century, people are chopping frogs' legs, you know, having fun with static electricity. There's all kinds of empirical laws. Benjamin Franklin calls them electron negative. Then there is a more systematic formalization of this. You have Faraday's universal law of induction. You have, you know, shoving magnets into coils. We see that there is a relationship between electric and magnetic fields. Of course, Oersted earlier, I mean, people knew about magnets for a long time. Natural lodestones were used for navigation, but the relation between current and magnetic field was discovered later by Oersted. And then you have this, you have Maxwell come in and say, and put this all together in this mathematical formalism, and just purely now, at this stage now, the feedback loop closes, we say, theoretically, these equations are inconsistent because they don't allow for the case of when we don't have a steady current. And so Maxwell just postulates that there is another term in here, the displacement current, which must be chosen to be consistent with charge conservation. And we'll complete Maxwell's equations next time. We're going to talk about the relations. All right?